Hello?
Hello.
There we go. Is it me you're looking for? See, yeah. I'll keep my day job though. All right, now, can continuity add a number? That means, is it going to be continuous at a specific number? The function might be discontinuous everywhere. There might be all kinds of spots in which that it's not going to be continuous. One example of that would be a reciprocal trig function, like cosecant. Okay, cosecant, a secant, a tangent, a cotangent. Okay, tangent is irregular, but reciprocal. That one's also undefined, right? That one's going to be undefined at points. So there's all kinds of points in which that those functions are discontinuous. But we're only going to be pointing to certain spots now. So now determine if this function is continuous at the numbers -2, 0, and 2. So first, okay, now we need to talk about what? Domain restrictions. So now, easy test for domain restrictions. So the first thing, I cannot have 0 in the denominator, right? Yes. No 0 in the denominator. So take whatever you have in the denominator, set it equals 0. So that's what I'm going to do. I'm going to say x squared minus 4 equals 0. Okay. This is going to give me my domain restriction. So now at this point right here, I'm going to say f that. And what are you going to get? X plus 2, x minus 2. There we go. That is my difference of squares again. That is my difference of squares. So I factored it, I got difference of squares, and when I set each one equal to 0, okay, so if x, right here, so if x is positive 2 here, this equals 0, right? If x is negative 2 here, this equals 0, right? But since this is a product, which is multiplication, anything times 0 is 0. So if either one of these things right here is equal to 0, that means the whole thing is going to be equal to
0.
Thank you. So I know that I'm going to have restrictions at, okay, plus and minus 2. So x cannot equal, so let's go -2 or 2. Okay? So it's not going to be continuous at those points right there. Okay. Now, look at the numerator also. Is that a square root? Dun, dun, dun. What can I not have inside a square root? No negative numbers, right? No negatives. No negatives inside there. So let's take a look. Because I have an x squared and a plus sign right here, okay, that x squared will do what to any negative? Make it positive, right? So if I square it, it will always make it positive. Okay, so that's going to be one thing that's going to help me out. So it's not going to hinder me too much there. But see this plus 2 right here? That plus 2, since it's positive, I'm adding. So from that x squared, I'm always going to get a positive. Okay, I'm either going to get a 0 or a positive number. But then from there, I'm going to add 2 to it. So since I'm adding 2, that means that no matter what I do, I'm only going to get positive numbers. Yes?
Yes.
Okay, good. All right, so since I'm only going to get positive numbers here, that means that I don't have to worry about that as a restriction. That's not going to give me a restriction. Now, let's take a look at 0. Can I plug in zeros?
Yes.
Does my math doesn't say I have a restriction at 0, does it? No. Okay. So if I plug in 0, I should be able to get a number, some number. I don't know what it is. So if I do that, it's going to be 0 squared, which is 0, right? So 0 plus 2 is?
2.
So square root of 2 over 0 minus 4. So there we go. It is a number. It is a number. It is not undefined. It is super. All right, good. Let's take a look at what a graph like this is going to look like. So, because those parts in my denominator, which is going to be my restrictions, my undefined. In this case, what am I getting out of these? You can say that. Say it. Asymptotes. Asymptotes. So we're going to get asymptotes here. Yep. We have asymptotes there. And we have a real value at 0. Determining whether a piecewise defined function is continuous. Okay. So continuous at 3. Okay. So now, this is super important. Okay. For it to be continuous, go ahead, you guys can do the hand signs for this. Go ahead, come on class. The left side has to equal the right side. And they both have to go to the same number. So the f of c, the middle number, right? The number that they go to, so the f of c, which is right in the middle, has to also be the same thing, right? So remember, we're talking about that roller coaster. Do I want a hole in that track? No, I want it to be continuous. So at that point right there, there's going to be no missing, no holes. So let's see what we get here. So if x is going to be less than 3, so let's plug in what it's going to go to at 3. That's going to be important. What it's going to at 3. Okay? So if I plug in 3, front row, can I plug in 3?
No.
No, I cannot. Can I do some math for it? Because I'm trying to find the limit as this is going to, right? I'm going to try and find the limit as this is going to. So, now, I'm about ready to say another one of those F words for this. Factor. Factor that. So what are you going to get?
X minus 3.
X minus 3 and? Very good. And it's all over? Very good. So what's that going to happen now? That's going to cancel. So that means it's still going to give me a hole. Okay? So it's going to be a hole at 3. In this case right here, it's going to be a hole at 3. But because this symbol, is it supposed to ever be equal to 3? Say no. No, because equal to 3 would have a line under it, right? So the limit of this one, so now I could go ahead and plug this in, right? So at 3, I get 6. So this is equal to 6. So the top one's equal to 6. So the left side goes to 6. All right? What about that middle? So when x is equal to 3, my value is 9. Okay. And now let's look at greater than. Greater than. So that means I'm going to be talking about my right-hand side. So the right-hand side of this function, I plug that in and see what I get. So the right-hand side of the function, it's going to be 3 squared is 9, minus 3 is equal 6. Now, let's see. The left side goes to 6. The right side goes to
6.
But in the middle, do they go to that same number? No, because that's 9, right? So there's a spot right there which is not continuous. For this to be continuous, that middle number has to also be 6. So, is this one continuous? No, it's not continuous. Okay? Okay, definition, removable discontinuity. If I could factor out my part of my function that gives me my 0 in the denominator, that is a removable discontinuity. And in the terms of a graph, the removable discontinuity puts a hole in my graph. What I mean by that, the hole in my graph means that it would be, you know, my graph is going to go, oh, come on now, open dot, and continue. That's a hole. Okay, so just at that single point, there would be a hole. All right, so I'm pretty sure you guys could read through this. Continuity at a number. Now, this thing is going to be a step function. A step function. So now you guys are going to do these on the calculator. I'm going to show you real quick. So in a step function, you go to the graph. Okay, you guys go to the graph on your scratch pad, and you're going to type this in because it is in the menu somewhere. I just can't remember where. So I just type it in. This is a integer. Okay, int, and then you're going to parentheses x close parentheses. Open, x, close. Hit enter. There we go. This is a step function. This is greatest integer. Everyone should have this thing that looks like these right here. Anyone not have that looks like these? int. So it's like abbreviation of integer. Integer, int. Anyone else? Anyone need help getting to this point? All right. So let's go back to my question. It said, is it continuous at 1? Okay, let's see where 1's going to be. 1 is right here. Okay, for you people watching on YouTube, you can't really see my pen here, but watch. There, right there. 1 is right there. So I'm going to do this thing on my calculator that says menu. I'm going to trace graph. So I can just go through and actually trace it and see where it's at. So at 1, let's see. So I'm just going to put in the number 1. Okay, the trace function is on. This is the trace function at upper left. Okay, so I'm just going to hit the number 1. So it says x equals 1. It pops up. Hit enter. There we go. So it gives me a value right here. It gives me a value. So at 1, my value, so if c is 1, my f of c is 1 also. Okay, so that's going to be my f of c, which would be that. So now, let's look at the graph carefully. The right side of this function goes to 1. The left side of this function goes to 0. Okay, this is where it is right here. It's 0 down here, right? So I could show you by, since the trace is still on, I'm just going to arrow over a little bit. Just arrow over once. So both left and right hand side has to go to that. So that goes to 0. So if you look at my decimals here, they keep getting closer and closer, right? So it's eventually going to make it. Oh, come on now. Why are you going up so little? Oh, don't you even. How many digits you going?
It will go. Let's click on.
Oh, there we go.
Nope.
Nope. See? See? No!
Oh.
Hey, let's try this. 1 is the loneliest number. There we go. So it gets close, but never makes it there, right? So is this continuous at 1? Say no.
No.
No, it is not continuous because what type of discontinuity is there? We talked about this yesterday. It's a Van Halen song. Wow, okay. You guys at least know what Van Halen is? No. It sounds familiar. Oh.
It sounds like Bon Jovi, but it's
Okay. Same time rate, but not as lame. Oh, anyway. Anyway, I'll put it on afterward. I'll make you guys listen to it. All right. Anyway, so it is a. Y'all got notes in front of you. We talked about it yesterday. Types of discontinuities. I better not find it before you people. Oh crap, you're right. It wasn't yesterday. It was the one before that. Dang it. All right. I was even going to give you like special prizes and be like, yeah. Okay, but no. All right. This is a jump. You guys remember the roller coaster? Yeah, jump. Okay. So, all right. So this is a jump discontinuity. That means right here, there is a open dot, but it's a closed dot here. So once it gets to all the way to here, it goes up to the next one. Okay, that's going to be a jump. Now you remember it, right?
Yeah.
Wow. Okay, see, I'm not crazy. I am old, but still, come on now. Anyway, all right. Definition, one-sided limit continuity at a number. So let the function be defined at the interval. So now, look closely at this. I want you guys to see this. So parentheses and bracket. Okay. Parentheses means that it is not including that number, where a bracket means it's equal to that number. A bracket is equal to. A bracket is the same as a closed dot. A parentheses is the same as a open dot. Then f is continuous from the left, add a number here. So it has to be equal to that number there. So the limit of the left has to be equal to f of c. So it has to be continuous from there up until that point. Okay, if it was parentheses, then that would be no. That would not, because it would be equal to the limit, but the f of c would not be equal there. Okay, all right, same thing goes for the right-hand side. So that would mean it would be equal to c, but then going to b here. So it would be continuous over that interval at that number. Yes?
I got a jump. Would that be parentheses since you're now at the
A jump?
Yeah.
Okay, so it would be like this. So it would be bam, like that, not equal to. So it'd be limit is here, right? So let's say, oh wait, no, I don't want that one. I don't want that one. I want something else. What do I want? I want, let's say that and jump to here, right? Like that. Okay? So, what is this thing saying up here? Yeah, continuity, right? So right now, it wouldn't be continuous. Now, the left side that I'm talking about this is not continuous. I'm just going to put not here. Okay? Because it would start over here, and it would be not equal to at this right here, right? So this would be my C. This is my A, and this is my, what's the other one? B. Okay. This one is not continuous. Where this one right here is, yes, continuous. Because it is including the C value here. This one is not because it's not including. Because we're only talking about one-sided. Okay? So a jump would be discontinuous here because I'm trying to look from the both sides, left and right. But since I'm only talking about left or right, left, no, right, yes. Does that answer your question? No, okay. So, no, because we're only talking about one-sided. So if there was a jump, somewhere in between here, then it would be definitely no. Because I need it to be continuous from point A all the way to point C. Does that make sense now? Okay, yes. So roller coaster, yay! Okay, so this is like right there at the end, you just like fall off. Okay, there's no like little track to get out. Okay, all right, anyway, a little bit more sense. Yes? Anyone else? Questions? All right, so determine intervals in which a function is continuous. Okay, a function, so this is actually all kinds of good definitions right here because you're going to talk about this, and this is going to like, you know, I put a star on your notes for a reason because if I had a highlighter for you, which I do, they're all in the back, you can get them in a minute. I would highlight these because you're going to come back to it later. It's part of the notes. Okay, this is some of the stuff that you're going to have to reference. Okay, it's one of the boxes. All right, so function is continuous on an open interval. Open interval means parentheses, parentheses, and continuous at every point in between. Okay? So that means that, you know, you're the whole roller coaster track, okay? Okay, everything in between has to be there. But you're not equal to either end. Not equal to, so open dot on both ends. So, continuous on an interval, so this is interval, which would be from here to here, okay, from A to B, okay, on the open interval A to B, and continuous from the right at A. So it's continuous over the open interval and continuous from the right, because it continues. So it's on the right hand side where it actually is equal to that point. Same thing goes to the other side. This interval, but this one's continuous at B. So over the open interval, so the whole track is going to be, you know, all good. Okay. So where are we at now? Down. Okay. Closed interval means bracket, bracket. That means that both end pieces work. So when you go get on the ride, you know, you got like the little safety thing right there. Okay. And when you get off the ride, you also have the safety thing, but you're getting off at two different points. Okay. So both sides are good on both ends. Yeah, okay. Did that make sense, or did I just confuse the crap out of you? Okay. When we apply it some more, maybe, you know, a little bit. So here's examples. Okay, so this one right here, this is continuous at the left one right here, because it's continuous at A. So closed dot A, open dot here. So it is continuous over the interval from closed A to open B. This one right here is going to be continuous on, okay, open A, open B. So it is only continuous from there to there. So it's not continuous at the end. So open, open, yes, is continuous, and there is no like jumps or anything in the middle of there. Same thing goes here. So this one's going to be continuous. So from open A, close B, so it's from here to here on that interval. Okay, this one right here, same thing. So this one is an open interval, so it's going to be from here to here open. Even though it is defined here, this is not equal to the same one right here. It is defined, but the limit of this does not close it right there. That's what would have to happen. So it would be open, open. So this right here, it is defined on a closed interval. Okay, continuous on this, so it's closed here and closed there. That's important. Close, close. This is the one that you're going to be working with a lot. Okay, continuous on a closed interval. So that wording right there means that you're going to have a closed dot there and a closed dot there. And everything in between is going to be continuous. All right, determining whether a function is continuous on the closed interval. Okay, so for it to be continuous on a closed interval, what has to happen? No holes, no jumps, or anything in between. Okay, so for it to be closed interval, both ends also have to be equal, right? So in this problem right here, do I have some domain restrictions? Say yes. I do have domain restrictions, don't I? Because it is a 4 minus x squared, what has to happen? What is my domain restrictions? I can't have any, I can't get any negatives out of it, right? I can't get any negatives out of it. I'm not supposed to, right? So if I get any number greater than 2. So now I'm going to show you how to set up this to figure out your domain restriction. I know that this, so 4 minus x squared, right? Okay, it has to be greater than, no, I'm sorry, less than or equal to 0. That's how I set that up. Because inside the radical, is less than? No, I was right, greater than. Friday, why'd you try and correct me? Come on now. Okay, so this has to be greater than equals 0. Because less than would give me negatives. I don't want that. Okay? This has to be greater than equal to 0. Because if it was less than that, I get negatives, right? So this is how I set up my algebra to figure out my domain restrictions. You're going to see some wonky problems like this, and you're like, I don't know what it is. I can't look at it and see directly where it's going to be at. But, because every once in a while, you're going to get some weird fractions out of it. So like 7/5 or something like that you can't really look at and see, oh, hey, it's right there. You have to do a little bit of math on it. So if I was to do the math on this, let's go ahead. It's going to -4, so negative x squared greater than equal to -4, right? Divide by negative, so that's x squared. Now flip the sign. Less than equal to, my board doesn't like me today. Less than equal to +4, and then square root, so x is plus or -2, right? So square root of 4 is 2, right? Okay, so I should get plus or -2. Okay, so can it be equal to 2?
Yes.
Yes. The reason why I said that when I set up my problem, can the square root be equal to 0? What's the square root of 0?
Oh, you can't.
0. Square root of 0 is 0. Is that a number? Yes. It's not imaginary. I'm okay with that. So I'm good. So I'm allowed 0. Okay? So that's how I set this up right here. So mathematically, is it going to be continuous on that interval? Okay, think about it on the interval. So x, okay, is going to be less than equal to plus or minus 2 on a number line. I have -2 here. I have +2 here. Okay, so I have two numbers here, right? So, yeah? Okay, so when you guys set this up, okay, it's got to be less than, right? So if I'm doing this correctly, you know, I have to set it up. Whenever you have these inequalities in this right here, it's going to turn into, so x is going to be less than equal to +2, and it's going to be x is greater than equal to -2. So when we break those things up into this two separate parts, because we have a plus or minus there, right? Yes? So it's going to be the little arrow. I don't know if you guys ever saw this one. This is kind of like one of those weird things that I always do. Okay, so now from 2, it gets an arrow going that way. And from -2, it gets an arrow going that way. You use a symbol to figure it out. So the x has to go first for this to work. So from +2, it goes that way. So it's going to be a bracket at +2. And it goes this way. This, it has a bracket is equal to -2. And it goes that way. So it is applicable from there to there. Mathematically, I showed the algebra for it. Yes? Let's see what my graph looks like. Dang it, I didn't have the graph for that one. I thought I did. Theorem. I gotta do that one too. Dang it, there's another one there. Ah, crap, there's another. Where all these slides come from? I thought I only had like 2 slides left. Okay, they keep popping up. Okay, so now if you guys want to try and graph this, this is actually a hemisphere. When you graph it, it's half a circle.
Okay.
Yeah, it's a half a circle, so it's the top part of the circle.
Because it's weird because it can't be less than -2, right? Yeah. Because if it was less than -2, then it would be
Yeah, because when you square something, so let's say it's -3. -3 squared is positive 9. But it's 4 minus 9, which is going to give me a negative 5, which would be imaginary, right? That's where we get that from. Okay? Now, I've been talking a lot, and I was hoping to give you guys like a whole lot of time to work on your stuff. But how about this? Tomorrow, I will give you a day just for homework. I'll promise not to give you anything else. Okay? You come in early, right? Okay, get started. I can help you with everything. Okay, get everything done. Okay, so like I said, I'm sorry. I thought I was going to get through that quicker. Okay, I got a joke for you guys. Intermediate value theorem is a joke. Okay.
Nice.
I got a joke that goes along with this. Okay, so my joke for this is, why did the chicken cross the road?
Why?
I don't know. Okay, the question is, from one side to the other, I started off here. So you're like, hey, yo, this chicken. This is actually a real story, just so you know. So one of my students, okay, he was on my chess team for a number of years. We lived in Yuma, and he lived in a house. His parents actually had like a little house, and they had like an apartment complex right there too, on the main street in Yuma. So like the big street where everyone goes. Like it would be like living right on Indian School. Like your front door is a sidewalk on Indian School. Okay, same thing. Okay, but on this street he had chickens and ducks. And the weirdest thing was, I was driving by because I knew where he lived. I was driving by and there was just this duck in the road. I'm like, that's like the most random thing ever. You know, just a duck. And I was like, okay, there's a duck there. And so I went and asked him. He's like, oh yeah, my sister got a duck. And he's like, I hate that duck. And so the next day, you know, I was looking for the duck over here, but it wasn't. It was over there. Okay, so go along with that story. Did the duck cross the road? Do you know where?
Yuma?
Yeah, it's somewhere. But where did he cross the road? Did he go to the sidewalk? Did like seriously? Did he wait for the like blinking thing, or did he just like decide to cross it at some point? Okay, when I came back, so the duck is eventually over there. So what could I assume about that duck if I come back the next day and it's over there? He crossed the road, didn't he? That's the definition of intermediate value theorem. If I start here and end here, so if my duck was over here and it ended up over here, I could assume as somewhere he crossed the road. Somewhere he actually crossed right there. I don't know what the path he took. He might have walked all the way down to the stoplight. Some nice guy would actually like hit the button for him so he could walk at the crosswalk. I don't know. But this is the intermediate value theorem. If he starts here and he ends over here and it's continuous, at some point he had to cross it, right? That's what we mean for the intermediate value theorem. That's all it is. Okay? It was a big, nasty concept when I took calculus. I didn't know what the hell he was talking about ever. So, just remember, at some point, the duck crossed the road. And for that, I will go ahead and sign off. And don't forget, like, share, and subscribe. Okay? Tomorrow, I promise you guys. And, okay, so just in case, there might be